Cool. So here we have a very nice problem. I really like this problem. So let's go ahead and solve it. It says that there's a smooth semicircular wire track like this. The point to note is that it's smooth, which means there's no friction, okay? And it's in the vertical plane. Now, one end of a massless spring is attached like this, and there is a ring over here attached to this point, and the mass of that ring is m. This is what is given to us, okay? What else? It's also told to us that the natural length of the spring, let's say L, is 3r/4, and the spring constant K is mg/r. Okay, that's it. Okay, this point is P. So the question says, consider the instant when the ring is making an angle of 60 degrees. Sorry, the spring is making an angle of 60 degrees vertical. Consider this instant. And the question wants us to find the tangential acceleration of the ring. What will be the acceleration of the ring in the tangential direction? Okay, so how do we do this? Now again, initially it might seem a little complicated, but like as we solve this, you'll understand it's very simple. It's just a simple problem of drawing the right free body diagram. Okay, so first we need to find the length of the spring, right? It's obviously going to be stretched right now, maybe stretched, maybe compressed, I don't know, but we need to find the force that the spring is acting or applying on this ring, right? For that, we need to find what the length of the spring is right now in this instant. So what do we do? How do we do that? Simple. Let's draw a line like this from the center of the spring, okay? I'm sorry, of this wire track, of this semicircular wire track. Now what do we know? We know that this length from here to here is going to be r, because it's given to us. That's the radius of this track, right? This length also is going to be r, right? So for sure it's in isosceles triangle, which means that if this angle is 60 degrees, then this angle also has to be 60 degrees, okay? But then if these two angles are 60 degrees, then this angle also has to be 60 degrees, right? Simple, because of angle sum property, which means that this is not just an isosceles triangle, it's an equilateral triangle, right? All sides are equal. So this tells us that, let me just remove this to make it less confusing, that this length has to be r, which means that the spring is stretched, because we know that the natural length of the spring is 3r/4, and this length is r, which means that it's stretched. It's more than 3r/4, or its extension x at this instant, let's say x is that extension, is r/4, right? Simple. It's r minus 3r/4, so r/4. Fine. So this gives us a better idea of the situation. This tells us how much the spring is being stretched. Therefore, it's pulling in this direction. And now we know in which direction that this, the ring is going to move. It's going to move in the downward direction. Fine. That makes sense. Now, let's draw all the forces. Okay. Obviously, I'm talking about the forces that are acting on the ring. Okay. So obviously there's gravity, right, which is acting downward, because this is in the vertical plane, so it'll be mg. There is the spring force, which is acting in this direction, pulling it in this direction. What else? There's another force, right? There's a force from the frame itself. And in what direction will that be? Now let's say that's the normal force. Which direction will that be? It has to be in a direction toward the center, because we can assume that it's like a very tight ring that's around this frame. So all the forces that's coming from this frame has to be in that direction, in that radial direction, right? So therefore, it has to be in this direction, right? So, and let's call this n. This is the normal force. Okay, and what are these angles? Let me draw this separately over here. If I draw let's say this is the ring. There's mg in this direction. This direction, let's call it kx, which is the spring force, and there is a normal force in this direction. Now the question is, what are the angles? Right? We know these forces. These are all the forces. Is there any other force? No. As far as I know, no other forces. Now we need to figure out what the angles are. Let's see. How do we do that? What will this angle be? This angle has to be 60 degrees. That's given to us. This angle is also 60 degrees, which means that this angle, which is the angle between the normal force and the spring force, has to be 60 degrees. Okay, all right. What else? Now this angle and this angle, these two angles are interior opposite angles, right? Because this mg is acting in a vertical direction, that line is also vertical, that is this angle is also with the vertical, so therefore this angle also has to be 60 degrees. And that's it. Now our free body diagram is complete. We have all the forces and we know in which direction each of these forces are acting. Okay, so this is the free body diagram. Cool. But this is not enough. Now that we know the free body diagram, we need to figure out what? The tangential acceleration at that instant. Which means we need to find the net tangential force in order to find the acceleration, right? So how do we find the net tangential force? We have to resolve these forces in the radial direction and the tangential direction. So the radial direction is this direction. Let me draw it like this. This is the radial direction, the direction in which the normal force is acting, right? And the tangential direction will be somewhere like this, a direction perpendicular to the radial direction. Now, how do we resolve the forces? Now, first, we need to find the angle between mg and the tangential direction. How much will that be? How do we find that out? Simple, it's easy, right? We know that this whole angle, let's say, let me dot like this. This whole angle from here to here is 60 plus 60, which is 120, correct? Okay, and you know that this angle from here to here is 90 degrees because that's the angle between the normal and the tangential direction, which means that this angle, let me use a different color. This angle has to be 120 minus 90, right? Because that whole angle is 120, this is 90, so therefore this angle has to be 30 degrees. Okay, fine. That means this angle is also 30 degrees. Correct? The angle that kx makes with the tangential direction. Any confusions? Because that whole angle is 60 degrees, we know this is 30, this is 30. And why is this important to us? Because we need to resolve the vectors. We need to find the components of mg and kx in these directions. Okay, so let me draw that over here. It will become more clear. So first let me resolve mg to make things simple. Mg, if I resolve in these directions, there will be one vector in this direction which is mg cos 30. Correct? And there will be another vector in this direction which is the radial direction, right? And that will be mg sin 30. Alright. What else? Then we have, let's resolve kx. Kx will have again two components, one in the tangential direction and one in the radial direction. So let's draw one more vector like this for kx, and that will be kx cos 30. Correct? Alright, and there'll be another in the radial direction, that will be kx sine 30. Right? Okay. Is that it? No. We're missing one more force, and that's the normal force. The normal force will be again in this direction. Let me write it like this. And in this direction. That's also radial. And over here there is kx sine 30. Right, now this is simple and clear. Again, one common mistake that people generally make is in the same diagram over here, people try to resolve those forces and it gets confusing because now you have mg and then you write mg cos theta, mg cos 30, mg sin 30, and there's mg also, and very often we tend to forget to remove the original force. So that's why it's better to draw a separate diagram with only the components and not the original force. Now this is again complete, right? These are all the forces that are acting on this body. Cool. Now what does the question want us to find? The question wants us to find the tangential acceleration, which means we can see that the net tangential force in this direction equals kx cos 30 plus mg cos 30. So let me write here ft equals kx cos 30 plus mg cos 30, correct? So we have ft, right, which is the tangential force, that is equal to kx cos 30 plus mg cos 30. So I've written that over here. Yeah. Now let's just simplify this because we know these values. We know k. What is the value of k? The value of k is given to mg by r. Okay. X is already given to, that's the extension. We know that is equal to r by 4. And cos 30 is what? Cos 30 is sine of 60. This is how I remember it. And that is root 3 by 2. Right? Okay. Plus we have mg cos 30 again, which is sine 60 again, into root 3 by 2. Right? Cool. Of course, r and r cancelled. What we have? We can take mg root 3 by 2 out common, which we have 1 by 4 plus 1, which is equal to mg into root 3 by 2 into 5 by 4, which is finally equal to g 5 root 3 by 8. Now this is the final tangential force, but what do we have to find? We need to find the acceleration. And that's fairly simple. Acceleration is just the net tangential force divided by the mass. So at, finally we get at, which is the tangential acceleration, equals g into 5 root 3 by 8. That's it. This is your final answer. So here we have a nice common type of problem. It's called the banking problem generally. So this is important because it involves a lot of concepts. There are free body diagrams, there is resolving vectors, there is pseudo force, there is friction, a lot of things, and you have to combine all of that to get the answer, right? Cool. So let's quickly solve this. So what does the question say? The question says that the speed is 36 kilometers an hour. It's always better to convert this to SI units. So if you convert, that's 36 kilometers is 36,000 meters in 1 hour divided by 3,600 seconds. So it comes to about 10 meters per second. Right, and the radius of the turn, which is r, is given to be 20 meters. And what else? And the coefficient of friction is 0.4. Okay. Cool. Now, how will you solve this problem? Firstly, you'll have to think about what's happening. So it's a car or a cart or whatever you want that's moving across a banked road, a road that's not horizontal. It has a particular angle. So let's look at the side view of this banking. Let's say that this is the road. The angle is theta, some angle theta, right? Now, let's just draw it simply like this. Let's say this is the car. It has wheels like this. Okay. Now, how will it? What are the forces that are acting on it? Okay. And also, we'll have to figure out what will prevent slipping from happening. For that, let's just analyze the forces. Let's draw the forces. So we have mg acting downward, obviously. M being mass of the cart or the car. What are the other forces? There's, of course, normal force acting in this direction, perpendicular to the surface. Okay. What else? There's friction force. But in which direction is friction acting? We know it has to be parallel to the surface, true, but is it acting in this direction or this direction? Which direction? For that, that's why we have to check the cases. So the question is asking which of the following speeds are possible, which means we need to find the minimum and maximum speed, right? So think about it. If the car is going very slow, then how it'll want to move inward, right? It'll start falling inward, which means friction has to prevent that from happening, which means that it should be in this direction, right? And it should be the maximum value of friction possible. So the maximum value of friction is mu into n, right? Any low, because we are looking at the least value of speed. If it had a higher value of speed, friction will still be there, but it won't be the maximum value of friction, right? You're getting it? So for it to prevent, for friction to find the least speed possible, friction has to be in this direction, and it also has to have the maximum value, so which means it should be equal to mu n. Okay, what else? Am I missing any other forces in this? Now, there is one force I'm missing over here, because this is not an inertial frame. This body is accelerating, it's moving, it's turning, which means it's moving in circular motion. So we are in an accelerating frame of reference. So, and in this frame of reference, we need to apply a pseudo force in order to make sure that, the net force is zero, right? So what is the pseudo force? Well, because it's accelerating, we know that, let me draw this in this direction. It's technically accelerating in this direction with some acceleration a, because it's accelerating it's rotating in the horizontal plane, right? Which means if you go to the forces in this frame of reference, it has to have a pseudo force of m into a. It gets confusing if you draw both the acceleration and the force, so I'm removing the acceleration and I'm directly writing only the force. So in this frame, for it to have a net force equal to 0, it should be m into a in this direction, right? Cool. Of course, see, when I say net force is 0, I'm talking about in the vertical plane. This is the vertical plane, right? Of course, it's moving in the horizontal direction, but that's not what we're worried about. All the forces that I'm drawing are only in the vertical plane, right? And there is no movement in the vertical plane, so therefore the net force in the vertical plane has to be 0. Okay. Now what do? Now, simple. We just resolve all the forces, because you have multiple forces in multiple directions. There are different ways to do this. I like just to draw the angles out and write the forces. So let's quickly resolve all these forces. So there are two ways of doing this. You can resolve all the forces in the the directions which are along the surface and perpendicular surface, or you can resolve the forces in the vertical and the horizontal directions. Let's do it in the how will we do it? Let's do it along the surface and perpendicular to the surface. Yeah, okay. Now, what are the forces? Now, mg, if we're going to resolve like this, so this will become so mg cos theta and mg sin theta will be in these directions. Okay, fine. What are the other forces? Now, normal force. Let's resolve the normal force. So normal force is anyway in this direction, so we don't have to resolve the normal force. Perfect. We have friction in this direction. Again, need not resolve. But we have to resolve the pseudo force, which is m into a, right? In this direction, so that means the component in this direction will be ma cos theta. In this direction, ma into sin theta. So these are all the forces, and all the forces have been resolved. One common mistake that people generally make is when these forces are being resolved, they also write the original force. That is, they also add mg, for example, over here, and they get confused. Now they think that there's mj cos theta, mg sin theta, and there is mg. You should not do that. So a nice strategy to avoid this is, once you resolve the forces, don't add that force, just remove that force. So if you look closely, these are all the net forces. So now, because there is no movement in either of these directions, we can write the equations over here. We find that n stored over here, n is equal to ma sin theta, and okay. So now that we have these two equations, let's call them 1 and 2. Now, how do we move forward from here? Well, what are the things that we don't know? Now, obviously, in this first equation, n is equal to this, which means that we can substitute this n value in the second equation over here. Mu is something we know already. What we don't know is a and theta, right? M is, of course, the mass. That's simple. But we don't know the acceleration and theta. Now, what do we do? Well, what does the question say? Question says we have to find speed. How do we find speed with all this information? Let's go one by one. So first, let's talk about theta. How do you find theta? For that, the question has given us some information. It says that the road has been built in such a way, or it's been built in such a way, or it's been designed for vehicles going at 36 kilometers an hour, or 10 meters per second. What does that mean? It means that when vehicles move at this speed, the friction will be zero. There will be no slipping. This is what the question means. This is what this statement means. Which means that, so if I draw the diagram again, like this, if you look at the forces that are acting on it, it's mg, of course. Mg will be one of the forces. There will be normal force. There will be pseudo force in this direction. Let's call that ma. But there will be no frictional force, because that's how it's designed. If the speed is at 10 meters per second, if the vehicle is traveling at a speed of 10 meters per second, then there will be no friction. That's what the question says. So using this information, we can easily calculate the value of theta, right? So to find theta, what we do is we draw the free body diagram for when there is no friction, right? And this is that case. This is that free body diagram where there is no friction. And if I resolve the vectors and I write the equations, these are the equations I get. And then finally, using this one particular equation, I'll find that tan theta equals A2 by G. A2 is that acceleration in that case, in that ideal case where there's no friction. And that should be equal to V squared by RG. And that V is given to us to be 10 meters per second. So therefore, we finally find that tan theta will be equal to 0.5, or theta will be equal to tan inverse of 0.5. And using that value of theta, now that we have that theta, we input that in these two equations of 1 and 2. Now we only don't know A. right? So basically we calculate A. So using these two equations and using the value of theta that we calculate the value of A. But then now our objective is to find the minimum maximum speed, and this is the condition corresponding to minimum speed. So but A we know will be equal to V min squared by R, right? Just so that we're not confused, this A is a different value of A. So I'll call this A2. This is the value of acceleration corresponding to when V is equal to 10 meters per second, right? So that's the acceleration that we get. This A over here is the acceleration corresponding to when the velocity is minimum, right? Because this diagram over here is that condition, correct? This FBD is corresponding to that condition. So using this value of A, we can calculate the value of V min. So once again, this might feel like a lot of steps and a lot of algebra and so on and so forth, but it's actually pretty simple. It's just making sure that your free body diagram is correct, then making sure you're resolving in the right direction, making sure you're adding the right pseudo force, and then finding this value of A and therefore finding the corresponding value of the minimum speed. Okay, so now that this is done, now you might ask, fine, this is fine, but what about the maximum value? When is the maximum speed, or what is the condition for maximum speed? Well, if you think about it, see, when the body or when the vehicle is moving at a faster speed, there'll be more centripetal force in the outward direction, or rather you can say there'll be more pseudo force in the non-inertial frame. There'll be more pseudo force in the outward direction, and therefore this vehicle will tend to move upward, right? So for the maximum speed possible, the friction should prevent that motion, prevent it from moving upward, which means it should act in the downward direction. Now if I draw the free body diagram again, let's say this is the ramp, this is the road, it's at that angle theta. This is the vehicle, okay? But it's going faster now, right? So if I draw the forces, there will be mg downward, of course. There will be normal force in this direction. Well, there is pseudo force in this direction. That's fine, right? But because the speed is greater, the acceleration will be greater. So let's call it A2 or A3. Let's call it A3 so that we don't get confused. So pseudo force will be in this direction. There's of course going to be friction, but which direction will that friction be? Because it's preventing upward motion. It's preventing the body from moving up. The friction has to be in this direction. And because we're looking at the maximum value of speed possible, the maximum value of friction will act, right? Because we're looking at the maximum value of speed possible. So the maximum value of friction will be mu into n, and that will be in this direction. And that's it. This is the basic free body diagram. So just like in the previous case, we have to resolve all these forces now. All these four forces, get them, resolve them in the directions which are along the surface, perpendicular to the surface, and then find the equations, find two equations, and it's basically the same process. So as I said, if your free body diagram and your resolving is correct, then you should be fine. The rest is all simple algebra and calculation. So if you get those equations, we already know theta, right? That's simple. So what we don't know, or what we will find, is this value of A3. If we solve these equations, we find this value of A3, and we know that A3 will be equal to V max squared by R, right? Where R is the radius of the zone, and that's constant. So if we find A3, we know R, we can find V max squared, and therefore we can find V max. So this way we can find the minimum value of speed and the maximum value of speed, and we have to check if our options, or whichever options are within these values, and that's how you solve the problem. So what are our answers finally? So if you do everything that I said, you'll find that the minimum value of speed, let's say V min possible in terms of kilometers per hour, will be equal to 14.7. And this will be in kilometers per hour. You get 14.7 kilometers per hour. And if you find the maximum value, that will be equal to 44.1. And if you look at our options, you'll see that options A, B, and C, all three of them fit this condition, and only D doesn't. So this is a multiple correct question, which means that our correct answers will be A, B, and C.
For more videos and live lectures on the JEE, click on the subscribe button now.